Donc voici première unit 1 de chimie de solution. C'est appris en français au lieu de anglais, mais tout est la même chose, c'est juste les vocabulaires qui sont en anglais, on sont en français au lieu. On a commencé avec les solutions, so we start with solutions. And what is solution? Soluté, solvant. Solution is a mixture of non-homogeneous solutions. So anything that is heterogeneous is not going to be counted as solution. It's going to be a mélange. It's a mixture instead. So solution means homogeneous. Like everything looks similar. They are all uniform. They look uniform jusqu'au niveau moléculaire. So not to the super tiny detail, but molecular level is a solution that is homogeneous. There could be solvant, soluté. Soluté is the particles and solvant is the majority. And most of the solutions are not pure. So the pure solution does not exist. Most likely does not exist. Like air is not completely solution. There is stuff like azote, O2, CO2, methane, water, argon. In the water there's salt. In acid there's iron and carbon. And then there's stuff about saturation that we have to know about solutions. Saturation is all about how much solute it is in the solution. So if the solute is exceeding the solubility amount, so let's say salt, NaCl, 36 grams can go into 100 milliliter of H2O. And if there is less than that, it is non-saturated. So non-saturated or insaturated, we should say non-saturated for anything that is below the saturation, the solubility level of that solution. And that is unique to the solvent, so that's for H2O. And if there's any more than 36 grams, so if there's 37, 38, then if it does not melt completely and there's precipitates, or actually solid that is forming in there, then that's a saturated solution. But then if there is more than 36, so more than the solubility amount, but that it is homogeneous, so it did dissolve, that means it is in a special case called sursaturé, which means these solids could form if there's a little bit of perturbation that is caused to the solution. So the solution is really instable and they can form a solid if you mix it or if you touch it. So it's not here directly, but we also have to know some stuff about concentration. And the concentration is all about conversion, and there's gonna be a lot of conversion stuff to do. There is the mole par litre, which is the molarité. Molalité is for soluté in the mass of solvent, and mass has to be in 1 kilogram, so moles per 1 kilogram. Percentage of mass is everything that has to do with the mass of soluté over mass of mélange, so the mass total, that which is a percentage. And then there is the rapport masse et volume, so partie par million or partie par billion. Be careful if it's like 10 to the 9 instead of 10 to the 6. If 10 to the 6 is million, 10 to the 9 is a billion. And this is also for mélange, so it's soluté over total. Soluté over total for everything except for molarité. But however, sometimes if the mass of the solute is very negligible, then you don't need to include it. But that's not the case for like air, for example, because nitrogen is not like a very, very big majority. Although it is the majority, you should include the solute in the total, so in the denominator. And everything else is just a rapport, and you can't really see it here in the pink, but it's gonna be just pourcentage rapport volume, so volume of soluté divided by volume of mélange, which is a bit rare to be used. And then there is masse volumique, so mass of soluté, or not mass volumique, mass par volume. So it's like treating apples and oranges as the same unit, kind of. That's what the prof was explaining about soluté, mass over a volume of mixture. And here's some sort of conversion that you can see. It's just all about making the top and bottom crossing out, so stuff where grams are crossing out with grams, soluté are crossing out with soluté, and solvant are crossing out with solvant, solution, etc. You always suggested to write down all of your what these grams are about. So in here I didn't write it, but I should write grams of salt if it's grams of salt, and conversion of liter to milliliter, kilogram to gram, very important, and then moles. And what a good trick to do here is to make sure that whatever unit you need on the top to make it on the denominator, and whatever unit you need on the bottom to make it in the denominator. So example was in Montreal, there was 116 ppm of water, where there's 116 ppm of calcium carbonate. Knowing that the mass volume of water is 0.998 gram per milliliter, how do you do that? And we'll need to find the mole per liter, so it's just conversion from grams over grams of ppm to moles per liter, where the liter of water, or the gram of water, need to turn from mass to volume. We use the mass volumic that they give you. So if you need to convert from mass to volume of a solution, that is not usually anything actually needs to be converted with mass volumic. So you need mass volumic in some cases. For the water, the molarité is 55.4. And mass volumic can change, but usually if it's a liquid substance or aqueous substance, it's somewhere around 1. It could change 1 gram per milliliter. And exception is mercury. Mercury has exception of having a 13.6 grams per milliliter for the mass volumic. For solids, it differs from solids to solid. Some of them are as big as 19 grams per milliliter. Some of them are very small, like 0.33 grams per milliliter. It's all about sont tous à cause des microbules, des poches d'air microscopiques dans la structure qui vont changer la masse volumique. Donc ils vont avoir beaucoup de volume mais très peu de masse. And 1 gram per minute is also 1 gram par centimètre cube, and it is for the l'eau pure à 4 degrés apparently. Soluté and solvant. So soluté and solvant, it's a concept that needs to be maîtrisé. For a solution to happen, you need to first break down the soluté, which requires energy, and then also to break down the solvant, which also requires energy, and for the new interaction between le solvant and the soluté to happen. And for solvant and soluté to happen, that will release energy. So if there's a question about where does it release energy, it's when the solvation happens. So soluté with solvant, interaction entre une partie de solvant et une particule de soluté. And there is polarity, so charge distribution in water, that some of them are polar. And there is about why electrolytes, strong electrolytes like iron and compounds sometimes don't dissociate, is because the water trying to attract these ions are not as strong as the ions themselves interacting with each other. Donc l'attraction électrostatique est plus fort que les électrons, l'eau qui attire les ions. Si ce n'est pas assez fort pour séparer les forces oh my god, how do you say it again? Électrostatique, yeah, I just said it. Les forces interaction de soluté électrostatique, si elle est plus grande que l'énergie, anyway, between the water, it will not happen, so the dissolution will not happen. That's the reason. It will not dissociate. So, par exemple, les diamants sont des bonds covalents, donc les IMF vont, quand les IMF vont break down les diamonds, ceci n'est pas favorable à cause qu'ils nécessitent beaucoup d'énergie pour overcome this lien de ces bondes covalentes, donc il y a peu d'énergie qui est donnée. It's all about redonner de chaleur ou prendre de chaleur. Donc toutes ces forces qui vont se faire prendre de chaleur, prendre de chaleur. Yeah, anyway, it's pour rompre les solutés et pour que le solvant accueille les nouveaux liens avec les solutés qui se sont rompus. Donc on a fait des expériences pendant le cours. On a vu que le sel, il était en isolant. Si le sel, il est en phase solide, il faut faire attention, il n'y a aucun transfert d'électricité. Et lorsqu'il était mélangé dans l'eau, là il y avait beaucoup d'énergie à cause qu'ils étaient des électrolytes forts. Sucre, il n'y a aucune. Ça va être plutôt un mélange hydrogène. No, it's not really hydrogen, but wash is really good, also ionic, and HCl is also really good because it's acid form. On va voir c'est quoi les acides forts plus tard. And then on a le sucre. Il faut savoir qu'ils vont dissocier, mais ils vont pas ils vont dissoudre, mais ils vont pas dissocier. Dissoudre, which is dissolve, or just say like melt. Well, it's not melt, but dissolve. It's the molecules themselves that are going to be broken down, but the ions are not broken down. Like the atoms themselves, the ions themselves are not broken down. So dissociation is all about ions. HCl is a very good conductor parce que c'est un acide fort. Il faut mémoriser quelques acides forts. Sulfate de cuivre, also acide fort. Ammoniac, il était capable, mais il est fait parce que ammoniac, it's a base faible. Yeah, so ammoniac is a base faible, and ammonium is acide fort. No. No, it's acid faible, sorry. So ammonium was H4+. Oh my god. NH4+, that's ammonium. And it's acid faible. Whereas ammoniac, which is NH3, there's no charge, and it's a base faible. So those are both faible. And then CH3COOH. So CH3COOH, acid acetic itself, is acid faible. However, if acetate, so the ion COO- itself was combined with another ionic, well, this is going to become ionic. So this guy is going to be a strong for electrolyte fort. Il faut savoir classifier les électrolytes forts, électrolytes faibles. Interaction of a sugar and water is just some polar stuff going on with water, that's it. And sugar will not dissolve completely because their force within themselves are not favorable compared to the water trying to break them apart. Yeah, because the covalent bond of sugar, they have a covalent bond of the sugar that are too strong for water, and that is not favorable, and water are not able to break those. Now, électricité is a mouvement organisé des charges électriques, not électrons. Il y a des électrons dans le métal, dans le solide, mais pas dans les solutions. Dans les solutions, c'est des ions qui fait transfert, qui font des mouvements organisés, des charges pour traverser, pour faire l'électricité, pour que le courant passe. Ça va aller des anodes vers les cathodes, toujours de négatif vers les positifs. Et ce sont des électrons de valence peu retenus, donc peu tenus sur leur axe, qui vont sauter et aller facilement à un autre métal. Is it only to metal? But that's in the metal. I think the électron qui saute, c'est seulement pour les métals. Yeah, so l'électricité, l'électron qui saute sur une autre métal, c'est seulement pour les solides, c'est les métals qui vont conduire le courant. Anyways, les solides n'ont aucun mouvement, donc vu que aussitôt que vous voyez qu'il y a du solide qui est en rapport avec une question, même si elle est en électrique fort, si c'est solide, il n'y a aucune électricité, il n'y a aucun courant, donc il n'y aura aucune conductivity. Donc, pas tous les... now we're going to talk about electrolyte, right? Yeah. So, électricité... So, dans l'eau, c'est les ions qui déplacent au lieu des électrons. And electrolyte is one of the most important stuff, you know. Électrolyte se dissocie complètement ions. Les électrolytes forts se dissocient complètement ions lorsqu'ils sont dissolus. So, as soon as it dissoudre, as soon as it melts, well not melt, but as long as it dissout dans l'eau, it will be dissocié et fait les électrolytes forts. So here are the acids that you need to know. HBr, HCl, H2SO4, HI, HClO, HNO3. So there's nitrate, the big one, and ClO4 and SO4, the big ones. The rest are the small ones, HI, HCl, HBr. So HNO3, so nitrate, HCl4, ClO4, so peroxide, not peroxide, perchloric acid, and SO4 2-, so that's sulfate. So those are acids forts, and all the ionic composés ioniques are electrolyte fort. Electrolyte fort equals acide fort, composé ionique. S'ils sont dissous, s'ils dissous dans l'eau, ils dissocient complètement. Et tous les composés ioniques ne se dissouent pas. Yeah, so pas tous les composés ioniques se dissolvent. So not all the composés ioniques solid will dissoudre, but they're still electrolyte forts. However, even if they are in a solution, if they are not able to dissolve, they will become precipitate, which is important for a réaction précipitée. So, électrolyte faible se dissocie ou s'ionise partiellement dans l'eau. Only partial amount of these molecules or ionic, it's not ionic compound, only the molecules faibles are all molecules, because if it's ionic compound, it's automatically electrolyte fort. And if it's faible, they will dissociate partiellement, so only a little bit, or you just need to say that they don't at all, because in majority cases they don't, in the drawing diagram, for example. And ce sont tous les autres acides et les bases faibles. Et on ne dit pas les bases fortes parce que les bases fortes sont des composés ioniques normalement. Un exemple de base faible, ammoniac NH3. Et quand il réagit avec l'eau, soit qu'il reste tout seul ou il devient ammonium, which is NH4+, which is a base faible, acid faible, it will become an acid faible. So acid and base, all you need to know is that acid is something that will give a H+ ion. So anything that gives a hydrogen plus ion that gives this is an acid. And anything that takes away, anything that receives the H+ is a base. So if it received it, well, it's a receiver of the H+, so it's the base. And whoever that gives the H+ is acid. Non-électrolyte. Did I go over everything? So the non-electrolyte are all the hydrocarbures, so H and C, so methane, ethane, that's all I know. There's a lot more, but anything that has to do with like H4CH or like C8H, C3H10O8 or something. Yeah, and alcohol, all the stuff is OH, CH3OH. These are also like with C and H, carbon, like chain carbonic with OH, CH3, CH2OH, and sugar. So all the fructose, galactose, glucose. Hydrocarbures sont des exemples de Yeah, so these are the non-électrolytes. Type de réaction, il y a précipitation, acido-basique, and oxydation. Where's my stuff? Yeah, so dissolution is when there is something that becomes aqueous, and dissociation is when something becomes into their ionic form, when they became ions. So that's what I was talking about, why some stuff are ionic but don't break. That's because of their force entre eux, basically, the Ag and Cl. Well, Ag and Cl, they will break, but not... Yeah, so AgCl will not break. These will not break. They are too strong. But AgNO3 will break. So they do separate in water. And that's all from the periodic table that we can see if we do not memorize stuff. So, trois types de réaction. Précipitation is all about forming solid as soon as you see a solid. And this is one of the most easiest one to determine, I think. Because you can turn it into équation ionique nette, which I'll talk about soon, and if there's formation d'une composée qui ne dissocie pas selon le tableau périodique et selon les autres connaissances, donc ça va être précipité. Acido-basique is transferred to H, so one H plus is given to another one that takes the H plus. Oxydoréaction is anything that un agent oxydant perd un électron et agent oxydant prend un électron, agent réducteur perd electron. So reducers will lose electron and oxidants will take electrons. Oxidants, they will take electrons. So stuff like oxygen, they take electrons, right? All the metals are reducers because they give away electrons. So whoever that gives away electrons is a reducer. Just memorize that metals are usually reducers. So anything that will lose their electron, we can say that they lose their electron because initially they are atomic. They're atomic, so there is all the electrons they have. But then here, they will become a compound. That means they have an exchange of electron. That's why. So it's no longer... Oops. It's no longer a neutral state. So neutral state to oxidized state. Here example, again, MgS becomes Mg with 10 electrons instead of 12 electrons. Now, the type of so these are the equations. Molecular is everything that shows all the states, all the compounds, all the ions. Well, not ions, but the molecules. And here, it's really, really important to balance it. So you have to make sure that everything is balanced completely. And then you can go into ionic complete, which is dissociating everything that dissociates. So what does dissociate is all the aqueux that are électrolyte fort or, électrolyte fort, so composite ionic, or acid fort. So everything else, you keep them as is, you don't dissociate them. Only dissociate the ones that are electrolyte fort. And ionic net, you will basically cross out all of the things that are the ion spectateur, so things that are just hanging in the solution, basically. And everything else that does become a precipitate, for example, will the product have to have reactants for those to happen. So those are the real reactions that are happening. Dissocié ou pas, it's all about électrolyte fort. Électrolyte fort, dissocié. Everything else does not. And even if it's électrolyte fort, make sure at the product that it is selon le tableau périodique. So on the tableau périodique, it will tell you if stuff are or not being dissolved. So anything that dissolve or not is all about if the water force is able to break those interactive force between the ions or not. If it is not able to, then it will stay as a solid. So the periodic table, there's stuff like SS, so it depends on the concentration. If it is SS, L means there's a precipitate forming, so those are not soluble. So a tableau that you can use to memorize all of these is when for solubility rules, there's a table like this. Anything that is in the first group, cations and NH4+, there's no exception, they will definitely dissolve. Cl, Br, I minus, these will also dissolve, except for a few exceptions as well. But then these are also really soluble, so C2H3O2, CH3, so acetate, acetate, bicarbonate, and nitrate, NO3 minus, and chlorite, ClO3 minus, and other stuff. But these are the contrary, so CO3 minus, carbonate, and I think this is chromate, CrO4 minus, and definitely phosphate is something that will precipitate often. And there are exceptions, so like we said here, the first group ions and NH4+ will not precipitate. They will always dissolve. Yeah, so CO3 minus, PO4 minus, OH minus, S2 minus are usually not soluble. And acetate, NO3, and H4+, and first groups are all usually soluble. So one thing to note here about, where is it? These guys, the Linus that we used, the Linus was able to show us the slope and the intercept of a graph, and as well as the standard deviation, écart type, incertitude, they call it incertitude, of the S, or the slope and the intercept. And these, what you have to do is to just look at the intercept and the incertitude, and the first number for that incertitude will be kept and everything else will be turned into 0. And what you do to the original value itself, which is the signal, is to turn everything into 0 except for the lowest position of the decimal. So not decimal, but units, the tenth, the hundred, the thousands. So the one with the least is the one for the only sig fig in the incertitude. And that's how you build up the answer. So answers should follow your incertitude being 1 sig fig, and your values themselves following the decimal place for those. And of course, do not forget the unité. So this one was a droite for conductivity. So conductivity over concentration. Conductivity is mu big S divided by, what is this? Centimeter. Mu big S divided by centimeter. Mu S divided by big centimeter. And this one is mol par litre. And everything else follows that logic. Anything that is in the... So intercept is mu S divided by centimeter. And the slope is, well, that divided by this. And then the incertitude also have the same units. So you can just write everything and then put the unit à côté. Yeah, what we need to know about the graphs is to just make the titles... actually not title. The equation could be used in form with each of the variables. And this is the équation ionique net practice that we were doing. To make ionic net equations, and it's all about the same principle. Everything that precipitates will become S, and their reactants should stay. Otherwise, there is no reaction because they're all just ions floating in the liquid. So there was a question: 42 milliliter of a solution that was mixed in this amount of solution which with another concentration, and they're going to ask for what is a précipité and what is the mass of this précipité and the concentration of these ions, a very typical question like this. And the first thing to do is to write down your equation balancer. So balance your equation, it's probably most important part, and after that find the quantity of each of the reactants. So the reactants mole, number of mole, and then fill them into the tableau already. The products have 0 for everything. And then you have to find what is the limiting reagent. And the limiting reagent, there's a special way to calculate it, which is by doing this. So right now we have this amount of initial PO43-, and that is from making this graph. But in here I didn't do it, but the tableau here and the label over here, you just need to write the ions that are actually doing stuff, not the entire molecule. So if you follow the number of molecules, the number of ions instead of molecules, a bit like this. So right now we have number of ion equals to another number of ion instead of the entire reaction, because those things are a spectateur. So take out the spectateur, but do not forget all of your indices. I call it indice, but anything that says like a 2 right here, or like a 3 right here, or like a 2 right here. These are super important for you to calculate the concentration later on for the final product. And to find which one is the limiting reagent, there's a faster way, which is to use that amount of reactant times how much it will need for the product of each of these compounds. So there's 2 ions, right? This is the final product. These 2 are the only ions that are actually doing something. So the other ones are spectateur, they're garbage, and these are the ones that are doing the real reaction. And you want to compare one of the reactants of the initial moles multiplied by stuff ratio to find out what is the other reactant that is requis, that is required to finish all these reactants. So to finish all these reactants, this much is required. Is there that much? Do we actually have them here? Well, we have this much disponible. And if there's that much, well, that is required. We don't have everything. We don't have everything to finish these guys. So if these guys cannot be finished, are they limiting? No, they're not. That means PO4 is not limited. So CuCl2 is the one that's limiting reagent. And limiting reagent means that it will become a 0. So you use the same rapport, the number of mole here, use here, find with the ratio again to find your product. And this is the product number of mole. Turn the number of mole into mass. N equals to M over MM. So moles equals to mass over molar mass. And that is how you find, basically the entire table is already going to be found if you're rendu là. And the last step of finding the number of ions, remember, if it's spectateur, the number of ions is the same as the number of moles at the beginning, because they do nothing in the reaction. There's nothing going on. They will do nothing. They're existing there in the solution. They exist at the beginning. They still exist at the end. So there's nothing to calculate about for the spectateur ion. The only ion that you need to care about is the only one ion. It's usually just one that is left over. For example, PO43-. PO43 phosphate ion is still left over because it existed in the beginning, and it is not a spectateur, and there's reaction going on that loses some of it to become a précipité, and some of them will stay as phosphate ions themselves. So this is what you need to care about. But in this case, there isn't. But if this number of mole represents your ion, but your ion, let's say just invent something, have like a 2 here, then you have to remember to multiply it by that 2. Because in reality, for each mole of that molecule, there's 2 of phosphate, and you have to multiply this amount of moles by 2. Which in this case we didn't have to do. But remember that if there's indices like this one, you have to multiply by 2. Yeah, so that goes for the same too. For these ones, for example, for sodium, actually. For sodium, we had to do that because this one has 3 over here. You don't need to care about the coefficient. It's not a coefficient. We don't care about the coefficient. It's only for the tableau, to make it in the tableau, that you need the coefficient. But otherwise, you need only the indice to find out the concentration of that specific one. Remember units, remember your rapport, show all the work. And for when when subtracting this is really important. When you subtract here is where things actually lose the number of sig figs. So they are losing sig figs because they are actually counting the decimal places instead of the number of sig fig now. And if there's less decimal place, well, the sig fig will have to be accordingly to the number of decimal place temporarily for that subtraction. After that, you continue. Volume total is always the volume of those two that are added, and we say that on suppose qu'ils sont des volumes additifs, so they add up. So there's a graph, there's a curve that we need to study, and water is special because instead of going up like this, water will have to go down like this, and then there's the other curve, and that is because there's solid and liquid and gas. And for the same temperature, so this is pressure versus temperature. For the same temperature, if you go up, you realize that the more higher pressure, it will become liquid instead of solid. And that is the nature for water. And for other ones, if the temperature goes up, even if it's liquid, at one point it will become solid because it became compacted, and that is not water. And at the center right here, it's called point triple. It's the mélange of all the stage, and point critique is the one here, which is fluide supercritique. Basically, that's something that we don't know, we cannot distinguish if it is a gas or liquid or not. Between gas and liquid. And this pression and temperature is very important for boiling points. So you can look at the boiling point and melting point. This is what you need to memorize. Here is 1 ATM for boiling points, because these will represent boiling points. Boiling point 2. So boiling point first, it's when boiling point happens when the liquid vapor is the same as the vapor of the atmosphere, and that is because you don't need to know why, but there is a reason. The gas has to be made, there's bubble made, so boiling is all about bubble making. At boiling point 1, that means the vapor, the water vapor, the pression vapeur, the same as the pression of atmosphere. So if they're the same, water, there's boiling. But then if you add some solute, what's gonna happen? There's gonna be the courbe that becomes looking like this instead of the orange one. So the liquid phase will become more favorisé. There's more liquid tendency. So liquid tendency is favorized. They will become, making it liquid tenderized could actually also indirectly lead to the temperature of boiling point getting higher, and that is because for the same amount of temperature, well, the pressure is gonna be lower. So that's right here. At this temperature right here, this is the temperature. The first solution is already attained 1 atm, but for another solution that has solute in it, well, the vapor pressure is not as high. So what's gonna happen? You need a higher temperature for the pressure to be equal to 1 atm to boil. So these are the colligative properties. That's the courbe de vaporisation for the courbe of vaporization. So vaporization meaning that they will... Vaporization is not evolution. Vaporization is the surface that the hydrogen bonds are broken. I'll ask why. I'll later ask why the vaporization is going to be... How vaporization explains for being... Okay, actually that makes sense. Because if they become if they become less volatile, then they will definitely need a higher temperature for them to vaporize the same amount. So it's all about if they are able to become gas or not. The more solute you add, the less tendency for them to become gas, so it's gonna be slower. So the courbes should be lower, and therefore they will tend to stay liquid a bit in the larger tendency. So yeah, so water, the slope goes down. And now we're finally at The propriété corrélative. Propriété corrélative, there's 4 to know. Abaissement de pression de vapeur, that's what I just said. So the more solute you add, the pression of vapeur will become less. Just think that vapor will become less. Élévation du point d'ébullition. So if the vapor is less, then you need more temperature for that vapor to attain the pressure of the air, so the air ambiante. And therefore, the ébullition temperature will have to be higher. So it's plus difficile à bouillir. And abaissement du point de fusion, so the fusion point is going to be lower, so it's going to be harder to geler, harder to freeze. That's because of the formation, but you need to know why. The formation of the crystals are going to be dérangé by the solutes, but those are just details. Pression osmotique. I also have to ask if I need to know that. Pression osmotique is about solvent that pass from one to the other, from high concentration to low concentration. So the solvent of a solution will want to go from a higher to a lower concentration. Yeah, they have that tendency to do that. So water has tendency to vaporize because of their mixing nature. Yeah, so the vaporization is going up has to do with the concentration of the water here. So the evaporation, the speed of this evaporation will go down if the concentration of water go down. The concentration of this, of condensation, is the same as the concentration of the vapeur d'eau. So if the concentration of the vapeur d'eau, well, nothing changes by adding solutes. Adding solutes will not change the concentration of the vapeur d'eau in here. So the condensation speed is initially not changed. So adding solutes, condensation doesn't change, but vaporization change. They will decrease. However, at one point, because there's a lot less of water in the air here now, the concentration of this guy also goes down. So at one point, there's a new équilibre between the going up and the going down. Well, the going up, that became smaller, and the going down will also become smaller because of the concentration in the gas that is lowered. And that can be controlled by the temperature, because if you want... Yeah, so that can be controlled by temperature, because if you heat it up, although this became weaker, if by heating it up you try to make it back to its original velocity of vaporizing, and then again the gas didn't change anything, so the gas will just go down like that. But actually maybe gas moving more, not sure. Maybe ask that too. Yeah. So just the 4 principal ones to know: abaissement and augmentation. Abaissement of point de fusion, augmentation de point d'ébullition, and abaissement de pression vapeur. So they're proportional to the decrease of concentration in water, proportional to the gas concentration, nouveau équilibre. Yeah, but you don't really need to know the why. Yep. So now this one is the TB prime. To a point about evolutions when the vapor has to equal to the atmospheric. So that is at 1 atm. At the ocean level. But if you go up to the mountain, for example, because the pressure will be much lower, what's going to happen is, well, there is pressure and there's temperature, and it will go up like that. That's the cours d'ébullition de l'eau. But, however, if it was at a much lower, because that's 1 atm, and if it's on the mountain, for example, the pressure will go down. It will be like here. And what's going to happen, the temperature for it to boil will be much lower. So if there's a lower temperature, the pressure is also lower, And to attain that atmospheric pressure, the temperature doesn't have to be that much high anymore. So water could boil at like 60 degrees, for example, in a very high mountain. So now we can talk about, yeah, I is the factor of Van Clough. So I, very important to know, it's the property of colligative property of the measured one measured one over if it was a non-electrolyte. And this will usually be proportional to the number of ions formed. So if it's NaCl, it will be like 2. If it's K2SO4, they will be like close to 3. And it's all about colligative property over colligative property of observed versus over non-electrolytes. So if it's a 1, and non-electrolytes are always 1 because the colligative properties didn't change between the measured and if it was non-electrolyte, because it really was it really was a non-electrolyte. And the K boiling, Kb, the constant unit is Cg, a kilogram mole per mole. So as long as your delta T equals to I mk works in terms of units, then that would work. And K is a constant spécifique pour le solvant. I'm not sure if it's specific for temperature. No, I don't think it is. Huh? No, it's not specific to temperature. Donc ça change pas en température, c'est seulement pour le solvant. I'll also ask this just to make sure. So now we have the IMK, just need to plug in and find out. And also the delta T for all of them have to be a positive number. You always want to make sure that they become a positive number. So this is just what we saw. Same thing for water. For the glass, rompre the H bond. There's equilibrium between the going and the coming out of ice and water. But then sometimes, if the soluté is added into this water part, because we can't really add it into the solid because they're crystals and they will kick out solutes. Well, what's gonna happen? There's gonna be a lower amount that becomes ice. So there's lower tendency of this movement. It's gonna be smaller. And there's more tendency of going out because they're still melting. So the melting point also again is concentration of the ice. And then the becoming ice is the concentration of the solution, right? Like the liquid part. So if the liquid part concentration lowers, well then the speed of freezing also lowers. And if it freezes lower, the freezing point, if the freezing is gonna be slower, then you need a much lower temperature for the équilibre to happen again, so that these two directions are going to be the same. And here's where you need to make sure that it's F take away F prime. Here is B prime take away the B, just so the datas are not going to be negative, because somehow they do not want negative stuff. And Kf is the constant cryoscopic, also specific to solvant, and it's plus sensible si plus grand. So if K is plus grand and everything else is the same, let's say two solutions with the same amount of soluté, so if the number of soluté does not change but the K is changed, then that means a bigger K is more sensitive to the difference in solute in terms of the temperature that I give. So the variation in the temperature will be varied by how much solute will give in a more sensitive way if the K is bigger. So the U-tube Yeah, the pasta. The pasta, they were saying that they put salt in it and asking if that is because is that for us to boil pasta faster, but it is not. It's really for the flavor because the amount that it increases is very, very negligible. So for water, the Copic constant for boiling is 0.512 and freezing is 1.86 if I remember correctly. Yeah, 1.86. So some of the stuff that the grenouille, for example, does is that they will make their membranes and their organelles very saturated so that they will not freeze. So if they make it really saturated, well, the freezing is going to be slower, so they're going to require a much colder temperature for them to actually freeze. So by saturating their cells, they will become less likely to freeze and explode and die. U-tube is the membrane, so there's a membrane in between that allows only solvent to pass and everything else not. The osmotic pressure is the pressure right here for this rush of water to be pressed down and stop rushing in. So there is a rush of water because solutes are much higher here and the solutes are much lower here, concentration lower. So they want to go to the much higher concentration. But for that to stop, there is a certain pressure by the Earth's gravitational pressure for it to stop, and that's the pression osmotique. Also, probably don't need to know much more than that. Pi equals to IMR. It's probably not a very big... Yeah, so that's not something I really need to know. Yeah, so the E is, like I said, experience versus etheric if it was non-electrolytes. And usually it equals to the number of ions that are present. So for one molecule of something, if it dissociates to 2, then the I is going to be 2. If it's a compound, one compound became 3 atoms, then the I is going to be 3. And that number is going to be changed. Going to be bigger if the charge is bigger, or if the concentration of these ions in the solution is bigger. So if the concentration of these ions is bigger, or the charge themselves are bigger. So let's say this one, it becomes an Mg2 plus, and the for 2 minus, well, 2 plus and 2 minus have tendency to stay together a little longer than to be separated and in separate ions states. And that is because smaller ions, well, they have less charge are less attracted to each other than a big charge. So like a 2 plus and a 2 minus is more attracted to each other than a 1 plus and a 1 minus. So what happens is that their I will decrease. Instead of being 2, or I should say instead of being 1.9, actually, let's say 2 will become a 1.9, but then a 3, actually it doesn't matter. Yeah, so this one, let's say it's an NaCl, but for MgSO4, there's still the same number of ions, there's still 2 ions, but it will become a much lower 1.3, and that's the real data on the tableau. So that's what explains when stuff are getting smaller, and that's all about how much ions, how much particles is in there. So it these are fine electrolytes. I already explained it. So passer, dissocier après tout. So the ions sometimes will be approximation near their other ion partner and actually not end up that much separating. Now all about vitesse de réaction. So vitesse de réaction is stuff that are spontané. So vitesse de réaction is explained by delta of that concentration divided by time, and these are all proportional to these guys, actually inversely proportional to me, because this one stays 1, this one becomes a 1/2, like here, and this one becomes, we'll see, is a 1, this one becomes a 1/2, and pay attention that there's minus if it's a delta concentration over T syntax. If you draw it like this, if you write it like this, and it's a reactant, well, it's losing it, so you have to put the minus sign. However, that's not the case for when you calculate stuff. So when you do the loi de vitesse, v equals to k times blah 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 blah, you do not include the minus sign. And if it asks you, the question is asking you what is the velocity for it to lose, then you do not add any negative sign, because you're going to say, oh, this absolute value of velocity for losing, for the decomposition to happen, for that reaction to happen, for the reactants to disappear, etc. And here is the so there is so one of the courbe will go 2 times faster than the other one, going half its speed down, and that's all about the coefficients. So the coefficient here is a 2 instead of here is a 1, and they're proportional 1-to-2 ratio. And we can see that it is going slower, and the reason is because of the amount of concentrations. So if the concentration is less, well, the collision between them are less. So it's a little bit talking about gases, but you don't need to really know about, I don't think we need to know about that. And those there are units for the velocities and stuff. So instantaneous and average velocity. Instantaneous velocity is the delta c over delta t, whereas it's like you find the 2 dots and you find the slope of that. Whereas tangent is for the instantané. So moyenne is for delta c over delta t, instantané for the tangent. You find the tangent, you find the point in the middle, slope of that. Loi de vitesse is the concentration, delta d over delta t, could be plus or minus, but you are gonna use this one very, very primarily. So vitesse moyenne in here is used for a series of lots of reaction of the same nature, of the same substance, but in different concentration or time, or time, increments of time. They just average it up to see if it's really that one, because we sometimes need to make sure that's precise. Vitesse moyenne, vitesse instantanée, vitesse instantanée. And so K here, it's another K. This K is the constant de vitesse spécifique à la réaction et varie avec la température. So it's specific for this one reaction. K here is specific for the reaction and depends on the temperature. So temperature, reaction, specific, everything else, if anything changes, it's not the same one. As for the ordre M or N, well, ordre is all about how much that concentration is in proportion with the velocity. If it is 0, order 1, order 0, there is no proportion with the velocity. So no matter how much that concentration change, it will not change anything for the velocity. If the order is of 1, that means it is proportional, exactly proportional to the amount of concentration and the velocity. So if concentration double, the velocity double. If the concentration triple, the velocity triple. It's proportional. If it was a 2 order, that means the square of the concentration is proportional to the velocity. So if the square of a certain concentration, if the concentration tripled, let's say, and the velocity will become times 8, then that is order 2, because the concentration squared is every time increasing with the same rate as how much the velocity is increasing. Yeah. So let's say times 2 for the concentration, but you see a times 8 for the velocity. Well, you know that this... Oh, that's not a good example. What's a good example? 2 and a 4. Why did I put 8? 2 and a 4. So if concentration increases with 2 and the velocity increased, initial velocity, by the way, it has to be initial, and we're saying initial because of the graph. Just imagine the graph. In the beginning of the concentration, we're most precise and we're most sure about it. That's why we're using the initial. And the initial velocity, you look at it and how much is it compared to the other. Really useful way, I think, is to use this, although it looks complicated. It's really simple. It's just the definition of the velocity itself equals to k, and the concentration to the order, but over the one over the other. The first one being the first reaction, the second one being the second reaction. And every time in an equation, if they give you the m and the n, if they give you the order, it's even easier to find the new the velocity, for example, or to find the k, for example. Because if they give you the m, that means the velocity is proportional to the concentration by how many power. You already know that. So if it's a 2, you know that the concentration doubling will affect what? It will quadruple the velocity. If it is of reaction 1 and the concentration was cut down to half, we know that this one also, the velocity also will cut down to half, and that's something that we were looking at on the test. So when it cut down half, the other one cut down half as well. If it's a order 1, if it's an order so yeah, it was a one was ordre 2, and then the other one was ordre 1. So if one of them became half the concentration and it was of ordre 2, well then it will quadruple. And the other one became like half of itself, then that means it will also half the velocity. And half times half, well no, quadruple times half will become times 2. So times 4 for the x times 1 out of 2, so 1 over 2 for the y substance. Well, then you just multiply those two. Just multiply whatever this factor will do and this factor will do, and that will give what the velocity gives. So you can look at the inside of concentration to find those out if they're given the n. If the n and the m are not given, what we can do is to make sure that one of these concentrations is the same. So you build this equation, this one, of just putting things into this order. It's just velocity equals rate, the rate expression k times concentration. And every time you just make sure that one of the concentrations is the same, so that it will cancel out, like that. And after canceling out, well, you also cancel out k, and you have the velocity, and you have the concentration. So then what you can do is, wait, what did I do here? Yeah, find the m. So all of this power to the m is equal to that. So now you use log, so something equals to something to the power m. You just ln of something equals to m times the ln of that something, and bring the ln to the other side, ln of m to the other side, and you can find m, isolate m. That's the order. Or you can just use a tableau method. If that goes down half, it goes up 1, and this one goes down half, and this one also goes down half because this one didn't change. Well, then you know that they're proportional. So this guy right here, the reactant here, is of order 1. And if it went down, if it didn't change, went down of times 2, and this one went down of times 4, well, now you know that this guy is actually of order 2, because it's proportional to the square of that. And usually these orders will be of entire, a nombre entier or petit nombre entier, so it won't be fraction or negative, usually speaking. And these orders are only found experimentally. They're only found experimentally. So constant of vitesse has units, and those units are a very, very simple rule. M, molarité. S is a seconde à la moyenne. So everything is S seconde à la moyenne. And there's a seconde à la moyenne times molarity times nothing. So just S à la moyenne for order 1. So this is order 1. 0, 1, 2, 3, 4. Or N. That actually looks like an N. So M à la moyenne for the second. M à la moins 2 for the third. And that's it. No need to complicate anything else. Méthode de loi intégrée is about products that are made from a single reactive. And we're using un seul réactif parce que pour faire le intégral, c'est beaucoup plus facile avec un seul variable que plusieurs variables. S'il y avait 2-3 variables, ça va devenir beaucoup plus compliqué à intégrer. C'est pour ça qu'il faut utiliser un seul variable. Et la méthode de la voie de la vitesse intégrée, ce sont pour les ordres 0, 1 et 2. Je vais mettre le 2, je vais vous montrer le 2 après. So for 0, very simple rule, concentration de A est égale à moins KT plus concentration de A initiale. So the final concentration will equal to the minus KT plus the initial concentration right here. Just need to look at the graph and look at what that gives. And you can find the concentration of another given time, or you can look for the slope if they give you the initial and the final, and just plug in stuff in. But if it is linear, it's all about linearity. If it is linear by plotting concentration against time, well then that's a 0. That's an order 0. If it is linear when it's ln of that versus time, which actually gives the equation ln of A equals to minus KT plus ln of concentration 0, then that's of order 1. And if it is order 2, it's just a little bit different. 1 over ln of A equals to KT. Now K is positive now. Okay, suddenly the slope becomes positive. Plus 1 over the concentration initial. So the concentration right here, initial. And that is of order 2. And these are all going to be one reactants. Which basically means that if it is of 0, of order 0, it's literally just K that's left over in the velocity, because the component, the composant, or the reactive is of order 0, making it just equal to 1, and there's no job for that guy. And we have the velocity, so the velocity rate is basically going to become K. Yeah, if it's order 0. That's why the unit is going to be masala by molarité moyen S moyen, because there's no concentration stuff at all in the ordered 0. Ordered 0 is very just V equals to K. Okay, so these are the benefits. Yeah, so remember that these ones for the order en vitesse is basically K ln of A. Did I write that? Nope. What did I write? K A, that's it. For the second order is K A square. And the first, 0 order is just K. Yeah, it's just K. Now we're talking about this tableau right here of the benefit and whatever else factors of initial versus integral. So if it's a vitesse initiale method, you need a few trials because they are not reliable for just only one reaction. Actually, it's also because you need more than one of the reactants number of trials to find out K, because you have too many inconnus. So let's say if you have 2 reactants, then you need 3 trials, modifying the concentration and stuff to find out the K, for example, or to find out another velocity. Actually, it's all for finding K, actually. Finding the order. Not sure, it's either K or order. He said K, but we'll ask if there's for order. And les données recueillies sont des concentrations initiales de vitesse initiale. Concentration initiale and vitesse initiale is all you need. So you need this, and you need this. And comment trouver les données en comparant les autres essais? Comparant les autres essais, I think it means with the tableau. And for the integrate, it's a lot simpler. The reaction, you just need only one. and to just see the courbe and see what kind of courbe that gives, and you just need to use the same courbe to plot it against the ln of that or the 1 over that to find out which one's linear. The exponential hierarchies only need 1. I guess it's a bit more secure for some reason. And the données recueillies, the concentration versus time. Everything can be done by these two valeurs. Whereas over here you need the concentration initiale and the vitesse initiale. So everything initial for the méthode de vitesse initiale. Yeah. And comment trouver les ordres? It's from the graphic using the linear, which one's linear concept. The demi-V is not going to be on our test, so I won't talk about it. Radioactivity neither. Yep. That's it. That's it for the first unit.